It's fantastic to be back speaking at GopherCon, and it's great to be at GopherCon in San Diego, because I hear that last time everybody had a blast, and I missed it, and I never heard the end of it at the office. There you go. It was great. I knew, I know. OK. I'm Filippo, and I'm here to tell you about how we keep bugs out of the Go cryptography packages. So I've been a maintainer of the Go cryptography standard library since 2018 on the Go project. And I've done this work over the years with Katie Hockman, Roland Shoemaker, Damien Neal, Nicola Murino, and many others. Some of the things we're going to look at today are my own work. Some of them are from the people I just told you, and some of them are from elsewhere in the standard library or from people in the community. Because, of course, this is an open source project. This is an open source project, and it is a collaborative effort. I was previously at Google in this role and as the head of the security team, and I'm now an independent open source maintainer, but we'll get back to that. Now, let's talk about cryptography. The Go cryptography packages are those packages that you use in your application to make secure connections, to encrypt data, so packages like crypto-TLS and xcrypto-SSH. And cryptography is kind of special. In cryptography, there really needs to be no bugs, because almost every bug ends up having security impact, most of the times leading all the way to security vulnerabilities. So we developed a set of techniques and practices to keep bugs out of the libraries and to get to a higher level of assurance for the correctness of these packages. However, many of these techniques are not specific about cryptography. So today we're going to talk about all of those reusable things that you can use yourself when in your code base there is some package that's particularly critical to your processes, to your systems, and to your business. There are often some packages where it's really important that they're robust, that they're correct, and that they're free of bugs. And we're going to see a number of techniques that you can go back and apply yourself, even if you're not working on cryptography. So we'll talk about techniques and technologies like memory safety, tests. There's going to be so much testing. And then we're going to talk about fuzzing, which is still testing, and then how to design safe APIs, how to limit complexity, and higher level things like how we focus on readability and how the maintenance itself is a technique that you can use for high assurance. But let's start with something that let's start with something easy. Memory safety is that property of a program where you can't do buffer overflows or use after freeze, where memory management is not going to cause bugs or vulnerabilities due to using memory in a way that's temporally or spatially incorrect. And I have good news. Everybody in this room, if you're doing Go, you already have memory safety. So pat yourself on the back. This is something you're already doing. And let's have a moment of appreciation for Robert Grissoner, Rob Pike, and Ken Thompson for designing the language like that. Great. And now let's talk about things that don't come for free. Let's talk about testing. In cryptography, we especially like large libraries of test vectors. We like to run so many tests against our implementations that we get high assurance of all of the edge cases. And we especially like when those libraries of test vectors are already available to us. For example, the ones that Project Whiteproof provides. Project Whiteproof is a project by Google named after the smallest mountain in the world, something about achievable goals. And a Whiteproof test file looks a bit like this. It's a giant JSON file of test vectors where it gives you the inputs, for example, the public and the private key, and the expected output, so the shared result that needs to come out of an ECDH computation. And we use this to test our ECDH packages. And there's just a lot of test vectors that test many different things, like a point with this coordinate in a precomputation of that step, and et cetera, et cetera. And then there are some that are about things that are invalid, points that are not on the curve that should be rejected. So each of these is another entry in a table-driven test that instead of reading all of these vectors from a Go file, where it would be unwieldy to have all of these test cases, reads from a JSON file and does each of these tests as it runs through the file. These are tested through a package that runs in our CI, which is a test-only package. This package does not have an API, does not have a main function, and it doesn't even have any file that does not end in _test.go. It exists only to get running CI, and when it runs, it will fetch these JSON files and run them against our implementations to make sure that they're correct. So how does it run them? Well, first, it downloads them from the same place where it downloads all of the other dependencies of our program. It uses go mod download to fetch the whiteproof repository like a Go module. And this is nice because it reuses the same caching mechanisms of dependencies that we already have set up in CI. And it means that we don't have these megabytes and megabytes of JSON files in the Go repo, where you would end up fetching them every time you want to run the thing instead of test the thing. So it fetches this, it JSON marshals them, and runs them against the implementations that it's testing. But sometimes we don't have available test vectors that are pre-prepared by a project like Whiteproof. For example, we recently wanted to refactor the internals of the ED25519 signature algorithm. A signature algorithm is a fairly simple function that takes a public key and a message and verifies a signature, or takes a private key and a message and generates a signature. So it's very testable. But at the same time, it has some edge cases which make it not completely well specified what it will do in certain specific cases. This might not matter much to many users, but to users that have a strong interest in consensus, like distributed systems and certain blockchains, it's really important that when they upgrade from Go 120 to Go 121, the two versions don't disagree on what's a valid signature and what isn't. So it was especially scary working on this package, because anytime we made a change, we had to worry, are we changing anything at all that's visible? And that was slow. So instead, what we did is that we went and made this large set of test vectors, just like the ones in Whiteproof, that we download with a similar mechanism, and that then we run against the ED25519 verify function to make sure that the behavior is always the same for all the edge cases we care about. The number of test vectors that came out of that is large, because there's a lot of edge cases. And since there are a lot of edge cases, each edge case dimension in a table, in a matrix, combines with all the other edge case dimensions. So what if that thing is in that situation, but that thing is in that other situation and hides the result of this and that? And you know how painful it gets to test all of the different configurations, because I didn't write those by hand, of course. So instead, what did we do? Well, just like you can import your test vectors and manage them like data, you can also do software engineering with your test vectors. So what we did is that we wrote a program that generates all those test vectors by combining all of the different possible edge cases. So for example, the input A can be one of these low order points, which are edge cases. But then also the input R can be one of these. But then it can also be encoded in a certain way, and then R can also be encoded in another way. How are we going to test them all? We're just going to nest 6 for loops and then generate a bunch of JSON and then run all of those and know that we covered every single possible state. An important thing is that this was just writing some code, some for loops. And this is something that we know how to do as software engineers. And doing that kind of engineering for your tests really pays dividends when you're looking for high assurance. So how do we know, though, that those vectors actually cover all of the edge cases I told you about? Well, we wrote tests for the test generator. And we have CI that runs tests against the test generator that then generates the test that go into CI, and we test against the ED25519 implementation. And this was just a ruse to win a bet about how many times I can say test on stage at GopherCon. The tests check that we get the right number in the right ballpark of tests generated, and that if a test says, oh, I have a low-order component A, it actually has a low-order component A. And then it goes in a delightfully recursive way to run ED25519 verify, the thing we are writing the tests to test, to make sure that it actually accepts and rejects the ones we expect to expect to accept and reject. So if we're working on the generator and it stops doing what we expect it to do, we probably introduced a bug in the generator. And if we're working on the library and it stops doing what we expect it to do, we probably introduced a bug in the library. So we use each other to test each other. But how do we know that we're actually testing for bugs that we don't have in the library? For example, one can imagine a library that does a specific thing that would be a mistake, and I think that my tests would catch that. But how do I know that the tests actually do catch that? Well, we wrote a broken version of the ED25519 library, and we used that broken version of the library from the tests of the test generator to make sure that it actually fails on the test that we expect it to fail. So this way, if we ever stop covering that edge case in our generated tests, we will realize, because the broken thing will suddenly start working correctly. So here we say, oh, these test vectors should break on this broken version of the library. And we run it, and that's how we get high assurance that the test vectors we have cover all of the different edge cases that we care about. Now, that works for something like ED25519 that is especially simple to test. Like I told you, it has just 2-3 inputs and a specific output, thumbs up, thumbs down. But what about things that are more complicated, like TLS? TLS is a protocol with a lot of moving parts, and it sends things over the network, and there's flows and messages and responses. We can't test that with just a JSON file full of inputs and outputs. So what we do is that we run those tests against a known implementation. Like we take OpenSSL, and if we're testing a TLS client, we will start an OpenSSL server, start the TLS client, connect to it on a port assigned by the test framework, and then do the TLS connection with a specific type of certificate or with a specific option, and then make sure that the connection succeeds. So what you're looking at is a test that does that for a specific type of certificate, ED25519 certificates, for example. And we wrote these helper functions that allow us to completely abstract away the part where OpenSSL gets started on a port, and then there's connections and bytes that move back and forth. And this is important because by looking at this test, you know what it's testing. You know that it's about ED25519, and it's going to configure this certificate and key on the server side, and then it's going to connect with a client over TLS 1.2 and then over TLS 1.3. And then it's going to clone the config and configure a certificate also on the client side. And then it's going to pass these flags to OpenSSL to say, hey, by the way, verify the client certificate this time, and make sure that we send the client certificate correctly. So writing all of these functions for ourselves to make it easy to run our own tests allowed us to write this test in, 20 lines, instead of having these 300 lines with command exec and starting OpenSSL and getting a port and opening a connection, which would hide what it is that we are actually testing. However, what happens when OpenSSL is not available on the developer machine, or if the version of OpenSSL is not the one we expect, the one that supports ED25519, for example? It's really hard to start OpenSSL every time you run a single test, also from a performance point of view. So what we have is, as part of that framework, there's a mechanism to record the flow of the connection. So the first time it starts OpenSSL, and then it records in files that look like this and are checked into the repository, the bytes that the client sent to the server, and then the bytes that the server sent back to the client, and then what the client responded to those bytes. So this is a recording of that one test that I showed you earlier, of one of the tests executed in that function. And the nice thing about this is that all of this recording happens transparently. And then, click. Because we have a recording con, which is an implementation of the netcon interface. And the netcon can be a TCP connection, or it can be a TCP connection with a recording middleware that will create the file, or it can be a fake con, which just makes sure that the bytes it receives match the one in the recording, then sends back what it's supposed to send back from the recording, and then checks that the final response is what came from the recording. And as you can see, it has a netcon embedded into it, and then flows, which are the things you saw in the recorded file. Then, when we want to update one of these tests, we have instructions printed to the terminal about which OpenSSL version compiled how you need to run these tests. And then there's a flag, because tests can take flags. You can do go test -update, and it will turn on this flag. And with that flag enabled, what happens is that it will first run the test from the recording. But if the recording fails, because maybe we changed something and so the recording needs to be recreated, it will rerun the test if update is enabled. But this time, it will run it using the real OpenSSL. It will write the file to disk. We will check the diff to make sure that eyeballing it looks right, and then we'll check it into the repository. And after that, we don't need OpenSSL anymore. The result of this is that we ended up with a lot of tests. If for each of those tests we had to write all of that boilerplate to execute a command and start something, we would have never written that many. But instead, thanks to the fact that we have this nice framework that allows us to very easily record things and have a low performance overhead to adding more tests, we ended up with a lot more. And this is something that I want to keep hitting on. If you make yourself tools and frameworks to create more tests, you will end up writing more tests. And that might seem obvious, but it wasn't to me, because it feels like test is this one-off thing, right? You wrote a feature, so you want to just write these tests to test the feature because you're shipping the feature. And you're shipping a feature, you want to get to the end of the day. There's no point writing a whole framework and library and tools to generate test vectors. You can just generate the test, throw away whatever you used to generate it, and move on. But next month, you'll add another feature, and then another one, and then another one. And it's the difference between ending up with something that's very poorly tested and a nightmare to modify, and ending up with this, where you have tests for every little thing you added, because every time it's just copy-pasting a few lines. So talking about that, let's talk about the foo test pattern. This is something that, that we took from the standard library. In the standard library, there's this pattern where if there's a package foo, there might be a package foo test. And I'm not talking about the foo underscore test inside the package. I'm talking about a completely separate internal package, which is dedicated to making testing package foo easier. So for example, here we're looking at Acme test. Package Acme is an implementation of the Acme protocol, which is what you use to fetch certificates from the likes of Let's Encrypt. So of course, we can't test the package Acme by testing it against Let's Encrypt, because these folks write Go, and they will come to GopherCon, and they'll find me. But so what we need instead is a fake CA server that we can start and run tests against. And importantly, this is not a mock. This does not say, oh, expect this request and send back this response. This is a fake, tiny little CA server that allows us to test our Acme client implementation. And since it's a library, we can instantiate our CA server with a testing.t. Because just like errors in Go are values, so are the testing.ts. So a testing.t is a thing you can pass into a library and then use it to, if the client does something wrong. So if the client sends an invalid request, the CA server fake will automatically call t.error and shut the error, the test down and detect that, even if the test itself didn't check anything. And the other thing it allows us to do is configure things like the issuer name, if we want to simulate a specific CA, or even resolve handler, where the CA sometimes has to make a HTTP connection back to the Acme package to verify some things. And we hide all of that in tests by passing the HTTP.handler directly to the fake CA so that it calls that to call back into our Acme manager. Now, I'm going to show you what a test that uses that Acme test package looks like. And this used to be a test that was hundreds of lines long because it was setting up all of the machinery to mock the requests. And instead, now, it's just a table-driven test where there is a prepare step, which configures both the manager, the actual Acme implementation, and for example, it adds something to the cache because we want to make sure that cache expiration works right. And at the same time, it has access to the Acme test server. So it can call those APIs we were looking at earlier to, for example, set the issuer name. So this is a test that makes sure that we can get a certificate, for example, .org, when there's already a certificate generated with these values and put in the cache from this CA. Again, every line there is relevant to the thing we are actually testing, because we've hidden all of the other things in our Acme test package, which allowed us, again, to write so many tests with so little boilerplate. And that's how we ended up with a bunch of tests, instead of ending up with, it's probably good. Now, the next thing is a technique that's not from the Go standard library, but from a package that uses the Go standard library, which is Agge. It's a very simple project of mine. It's just a file encryption tool. It takes a public key and a file and encrypts it, or a private key and an encrypted file and decrypts it. Super simple. But still, we want it to be well tested. And so here's the problem. How do we generate invalid files to test that they get rejected when the API is designed to only generate valid files? We don't want to extend the API of Agge to generate files that are broken more easily, because that's kind of the opposite of what it's for. But at the same time, I want to generate test fixtures that are broken in many different ways, that are missing a signature here, that have the wrong hash there, that have encoding error over here, because I want to make sure that I don't make a mistake and incorrectly accept something that should not decrypt successfully, because that would be also bad. So what do? Well, we wrote a completely new library that we call testkit that allows us to generate Agge files at a very, very, very low level of granularity, but with all of the helpers we need to make it easy to generate test vectors. So for example, you're looking at generating a valid Agge file with testkit. And it says, OK, let's make a new test file. And let's write the version line. It's a v1 file. And then let's encrypt this to the standard test recipient. It's a public and private key pair. Then let's sign with the hash, the header, which is important. And then let's encrypt the word Agge. That's the entire payload of the file. Then when generate runs, this is a main function, you might have noticed. So this is a tiny little program that, when executed, generates for me this file over here. And this is what we actually test. It's just a few key values saying expect success, because nowhere in that Go file we said this is a broken file, this is a valid file, so expect it to succeed. And this is just the hash of the word Agge. It's saying the payload, the thing that when you decrypt it, it needs to match this hash, make sure that it decrypts to the right thing. And then this one is the private key. This one wasn't even in the file I showed you earlier. But since we are making a library for tests, we can make ourselves little affordances, like when I say encrypt to this public key and you already know the private key, just make a note of the private key and add it to the test file. Don't make me repeat myself. And then this is the file that we just generated with the recipient line and the recipient and the HMAC that we are talking about. And another nice thing about this file is that this is not a Go file. This is a very simple, easy to parse key value followed by a file. So that means that this is completely language agnostic. And it can be used by any implementation of Agge to run their tests. So here's how we run those tests. We parse the vector, and then we make sure that, for example, if it says expect a armor failure, make sure that you actually get an armor.error using errors.as, because otherwise it means that something else went wrong. Something important here is that each test vector tests exactly one thing. We don't say, oh, well, if this test passed, it means that all of these features are working at the same time. We try to keep each vector testing the minimum amount of things, because that has two advantages. First, if it breaks, we know exactly what broke. And second, If for some reason an implementation does not support that feature, it doesn't have to lose other test coverage to skip that test vector. Why can we make so many different tests that are so granular? Because we have a library that allows us to very specifically generate each test vector, and the marginal cost of adding each new test vector is very low. I'm going to show you one last thing from this file that I'm very proud of. The vectors are imported just like any other module. Because you know how Go 119, I think, added Go embed, the directive to embed some files inside your package? Well, this package over here is a package that has only a Go embed statement that embeds into the vectors variable, which is a file system, all of the vectors that were generated for Agge. So we don't have all of those vectors, which are several megabytes large, in Agge. Instead, there are a separate module that is managed in the Go mod and imported with an import statement, just like everything else. And then we just do a read dir, as if it was on the file system, but we do it on the vectors variable that we just imported and manage with all our dependencies. And that makes me so happy. Now, the beauty, as I said, of having a library to do these things is that you end up generating tests for everything. So for example, if you encrypt with a password, there needs to be a number in the header, and it's a decimal. And can you think what can go wrong with a decimal number? Well, what happens if there's a 0 at the beginning and you're using parse int? Octal, correct. So, you know, one option was, oh yeah, that's a thing. I should make sure that I'm not using parse int. Do I use parse int? No, great, moving on with my day. But since it's so easy to generate another test vector, I made not one, but 2 test vectors. One that makes sure that it doesn't get parsed as decimal with a 0 in front of it, and one that makes sure it doesn't get parsed as octal with a 0 in front of it. So it goes back, it deletes the line that says 10, and writes back 010, and then another one deletes the line, and then writes back the line with 012, which is 10 in octal. Now, if by mistake I do introduce parse int usage, or another implementation uses something equivalent, one of these 2 will succeed when actually it should expect header failure. So they will run that test vector, and they'll notice the mistake. Finally, since these are Go files, we don't have to re-implement everything. We can reuse existing Go libraries to generate our test vectors. I wanted a test vector that made sure that if instead of the Agge armor, you used the PGP armor, it wasn't getting accepted. Why would it? I'm not sure. But I could write a test for it, so I did. And I just had to import OpenPGP armor in my test vector generator, write 2 lines, and I had a test vector that makes sure that if that were to happen, we need to expect armor failure. Great. So the result of this is that we ended up with so many tests in the test kit. I would have stopped at 12 tests, I'll be honest. But since I had that, it was almost exhilarating to write this code that didn't even need to be production ready, because it just needs to generate tests. So you can refactor and change the APIs and add helpers, and you say, you know what? I want to try generics today. And so you throw generics in there because it doesn't matter. It's something you can refactor again tomorrow, because it's just to generate tests. But the more you use it, the more you get tests. And these generate those language agnostic files I was telling you about, and those files get used by other Agge implementations. There's Agge implementations in Rust called Rage, and there are implementations in TypeScript and Java and Python, Page, and and each of them uses these test vectors, and there hasn't been a single implementation where we didn't find at least one bug by running the test kit. So it was good not only for the Agge implementation, but also for the Agge ecosystem that we had that test kit. And this is something that you can use yourself, because sometimes you will be rewriting a new implementation of something, or the team next to you is implementing the same functionality in another language. And you can share and reuse your work this way. The last thing I want to tell you about is the testscript package. This is a little gem. It's a re-exported version of command Go's test. Command Go is, the Go command, the one you type in your command line, Go space build Go space test. And how do you think the Go team tests the Go command? They test it with testscript, and a testscript script looks like this. This is a test from the Agme test. Agme also has CLI, so it's a command line tool, and you do agme-p to encrypt with a password, simple stuff. A test script file has two sections. At the top has a bunch of commands, and at the bottom it has files to set up in the environment before running the test. The beauty of it is that it's self-contained. Agme will need an input file and will need a key file. It will be very annoying before each test creating a temporary directory and putting the input file in there and putting the key file and then deleting them at the end, and then if we want to run another test we have to start over. TestScript does all of that for you. So it automatically creates that directory, puts those files in it, and then executes the commands you put in the script, make sure the commands pass, and then you can even say, hey, make sure that the standard output contains the word input. Make sure that the standard output matches the input file, because we encrypted it and decrypted it, and we want it to come out the same way. And make sure that nothing goes to standard error, because there was no error. Or if we decrypted with the wrong key, make sure that it doesn't decrypt and that it says this error on the command line. And we have a bunch of those to test the CLI. Just such a good tool. Great. So we talked a lot about testing, and we talked about all of the different ways we generate more tests for ourselves. And now we're going to look at one last thing about testing, which is sometimes you can let the computer generate the tests for you. And that technique is fuzzing. I'm not going to talk much about fuzzing in general, because Katie Hockman gave a fantastic talk last year at GopherCon 2022 about fuzzing for Go, and we have first-class fuzzing thanks to her in the standard library. So what I'm going to tell you about instead is about the techniques we use in the cryptography packages that specifically made fuzzing work for us. One of them is that we get a lot of value from differential fuzzing. Differential fuzzing is when you have two implementations that are supposed to do the same thing. For example, two ED25519 implementations. And you fuzz the input, and then you run them both and make sure that they agree on the output. If they don't, probably something's broken. And you can use that when you're refactoring something and there's an old and a new implementation, or when you're maintaining libraries in different languages that are supposed to do the same thing. For us, this is mostly done by the CryptoFuzz project by Guido Vranken, which found so many vulnerabilities in all of the cryptography libraries, and I'm happy to report that it only found 1 or 2 security vulnerabilities in the Go standard library over the years, and a few non-security relevant bugs. So I was very happy about that. But also, every time I get an email from Guido Vranken, I have a moment of, the next technique is weighted fuzzers. So fuzzers are great, but they're also not particularly smart. So they're going to just randomly throw stuff at the wall until something sticks sometimes. And for things like cryptography, they can't even do coverage guidance or patterns or dictionaries. So if you're fuzzing something like this, which is a large, large number that is so large that it spans 5 uint64s, there's no chance it will hit a specific value in quickly. So what do we do instead? Instead, we have these special fuzzers that will select much more likely some values that we know, as the developers, are more likely to hit some issues. In this case, I call them weird limbs. We call limb each uint64 you saw earlier. And weird limbs are going to be values that are more likely to turn up bugs than others. So for example, 0, -1, 2 to the 51 -1. Why 2 to the 51 -1? Well, because this implementation, we know that we do a carry after 2 to the 51. Doesn't matter exactly what it is, but the point here is that it's not completely black box testing. We're using some things that we do know about the implementation to help the fuzzer walk its way towards things that are more likely to cause bugs. These are not about specific bugs, though. We don't know what bugs we're looking for. We're just helping the fuzzer go towards areas where we expect more bugs would lurk. And this worked. We had a vulnerability reported to us that could only be hit if all of those bits at the top were set to 1 and all of those bits at the bottom were set to 0. The chance of hitting that randomly were 1 in 2 to the 154. That's heat death of the universe territory. Not happening. But instead, with the weighted fuzzer, we were able to reproduce that and find that without adding any knowledge about the vulnerability itself in a couple seconds by searching 2 to the 18 cases, because they were much more likely because -1 and 0 are weighted towards in the weird limbs. Now, sorry. I don't want you to get the impression that high assurance is entirely about finding bugs after you introduce them. We talked a lot about testing and how you can do a lot of testing and help yourself do a lot of testing to get a lot of assurance. But as important, if not much more important, is writing software such that introducing bugs is harder. And that matters also when writing interfaces for your own consumption internally. So we care a lot about the safety of internal packages and APIs. And that's because, like you heard from Russ Cox at the beginning of the conference, software engineering is what happens to programming when you add time and other programmers. That means that even if an interface is safe now, even if an interface is used correctly now, it might not be used correctly tomorrow by your teammate or in a few years by yourself when you move code around. So this is what I've been working on for now a couple years, has been refactoring the implementation of the elliptic curve packages so that they have a much safer internal API, even if what we expose to the user is still just signatures, ECDSA, and key exchange, ECDH. And those really need to be safe, and we made a new crypto ECDH package for that. But then we went and made the internal/NISTC and internal/bigmod and internal/Edwards25519 packages also much safer, so that when we write the ECDSA package and the ECDH package, we are not going to get it wrong ourselves. And I got a very good, unfortunately, a very good anecdote of why this is important by doing this work. Because doing this work, I moved some assembly that was being used in the old code into the new, safer package. And unfortunately, that assembly had an undocumented requirement. It had this, it needed a value to be less than a certain number. Was that documented? It was not. Was it respected by the old code? Yes, but not because there was a specific function that said, make sure this is less than n. It just happened to always be less than n because some code elsewhere was treating the number like that. So then I moved the assembly, and boom, now the assembly was breaking on some inputs because the number was higher than expected. Every other implementation didn't have that requirement, but that assembly one did. So was that interface safe? It was not. Was there a bug before I moved the code around? No, I broke it. I introduced that bug. But then we did, but then I did a post-mortem analysis on that because it ended up not being a security vulnerability, but just because we were lucky. So what I did is I went back and tried to understand, okay, why did this slip through our testing? And why did this happen at all? And the answer was, well, we didn't know what the requirements of our own code were. If you want to read the post-mortem, it's up there. And by the way, aren't those cute, the QR codes? I'm using Russ's tool to generate custom QR codes. Anyway, moving on. Next, let's talk about complexity for a second. The reason we have, by the way, that near miss was, the bug was reported to us by, guess who? Guido Vranken, who ran a fuzzer and found with fuzzing the bug in the internal package. Thankfully, again, it was not a security vulnerability in the ECDSA and ECDH packages, but that was too close for comfort. Anyway, we were saying complexity. The reason we have a I think I can say with confidence that we have a security track record that's significantly better than most other cryptography libraries. And the reason for that, though, is not that we are particularly better engineers or even the testing techniques that you looked at so far, because a lot of those techniques are used by most other libraries too. What allows us to have that security track record is that we target a subset of functionality that is significantly smaller than almost every other cryptography libraries. And that allows the complexity of the job to be much more manageable with the resources we have. And that's something that we've strived to do all the way from the original cryptography libraries designed by Adam Langley all the way to now. And it's trying to make sure that we don't add something unless we are sure that we can handle mentally and with tooling and over time the complexity of maintaining it and making it high assurance. And this is something that you can apply yourself to your code bases by being explicit about what is it that we're going to implement and what is it that we're not going to implement because it's not something that we can provide the assurance needed by this component on. And the way we do that is using the cryptography principles. The cryptography principles is a page, you can search for it, that says what are the Go cryptography libraries for. They are a tool to build secure Go applications. And to do that, they need to be secure, safe, practical, and modern in this order. That means that if something is not secure, we're not going to implement it. And if we can't make it safe, for example, by testing it properly, we're not going to implement it, even if it's the newest modern thing or if it's very practical to our users. And finally, there's no performance on that slide. Performance is part of practical. If something is too slow, it's not practical. It's not going to solve a problem for our users. But if something is fast enough, it's fast enough. We don't need to make it more complex and so lower assurance to make it faster. That's not our goal. And that gets to saying no. The Go cryptography principles are a tool that we use to say no, both in the sense that we use it to decide when to say no, and in the sense that we use it to justify it to the community and to the people we're disappointing when we say no. And that's because no is temporary. You can always change your mind next year, but yes is forever, especially for us because of the Go compatibility promise. But even if you don't have a strict compatibility promise, you know how hard it is to remove something. Now, though, what do we do when something was added and we wouldn't add it anymore now, we wouldn't like to dedicate resources to it? Well, that's where the torpedoes come in. Instant classic, this XKCD. So what we do is deprecations. And deprecations don't mean that we remove anything. Again, backwards compatibility promise. But it means that we will stop focusing all of these resources and this attention that I was telling you about on these packages and communicate to users, hey, we think that you should be using something else for one reason or the other. And we try to make sure that deprecations also suggest what you should use instead. Because it's bad to tell somebody, hey, stop doing that. OK, but I was solving a problem with that. What should I do? And so most of the times, the deprecations say, use that package instead, because that one we could make more secure, safe, practical, and modern. Finally, let's talk about something that might seem obvious. Readability matters a lot. Now, said like this sounds obvious, but at the same time, there is this almost meme that cryptography, since it's complicated, it's justified to also look unreadable. And I think that's upside down. The more complex programs should be the most readable, because you're already keeping all of that complexity in your head, and you're already dealing with all of this complexity that you have to think about and test and deal with. The last thing you want is also trying to figure out, what is that bit shift and masking doing? Is it just dividing by 4? Just write divide by 4. And this is one of the things that I care so closely about in the cryptography libraries, because I learned a lot of cryptography engineering by reading the Go cryptography standard library before I was in this job. And I care about them being a similar tool for the people that will come after me and replace me after I move on and become a scuba diving instructor. And and I want them to learn the same way I learned. So I make sure to write large comments that explain intuition behind things, and then you put useful names and explicit checks for things that I know will never happen, but that communicate. And then use types, like making a small structure for a uint 128, instead of just throwing around a couple uint 64s and say, yeah, I just remember that this one is the low bits and that's the high bits. This is a little slower. The compiler is not always happy with our readability changes, but that's okay. We're willing to take a performance hit to make things more readable, because making them more readable makes them more safe. And that's a goal, while performance is not. And readability helps me writing it, it helps people reviewing it, and it helps people learning in the future. So let's get to the last part of this. And I'm going to tell you, I said the word maintenance a few times. And I'm going to make the argument that maintenance is just yet another technique on par with the ones we talked about so far. Maintenance is the technique of continuously applying effort and new resources to existing code bases so that the assurance we can have in them grows. You also heard from, again, Russ in the keynote, that there is a special word in biology for stable, which is dead. Likewise, code rots if you don't touch it. So maintenance is the applying maintenance means, for example, going back to the office next week and using the things that you learned from this talk to add tests and add fuzzing and improve the APIs and improve readability of the most critical parts of your code base. Now, maintenance is also a topic that's very close to my heart for another reason. As I said at the beginning, I'm a full-time independent professional maintainer. And that means that I get to do maintenance like the one we talked about, and all of the testing and the improving assurance as my day job. And I get to do that thanks to this, thanks to the funding of my clients, who pay me because they understand the importance of this work to their business, and because this way they get access to me as an advisor. Well, folks, this is all. And as the Gen Z say, don't forget to like and subscribe. That's a link to that's a link to my newsletter. And then there's Blue Sky and Mastodon. And I do read all of my emails, even if I'm terribly bad at responding. Thank you very much.